Good evening, it's physics time. Today we have text problem 30-22 for lesson 39. As always, go ahead and get out a scratch piece of paper or a blank printout of the problem so you can follow along. Alright, so first up, we're going to be reading this problem statement. And for this lesson, it's especially important to figure out what is changing in time so that we can work with Lenz's law. But before we get into that, go ahead and pause the video, read through it, and write down some notes of what you might think is important for this problem. Alright, see you in a minute. Alright, so when I read this problem, there's a good number of things I pulled out. First is that we have a loop of wire. It's immersed in a uniform magnetic field. The angle between the normal vector, which is perpendicular to the area of our loop, or the plane of our loop, and the magnetic field, is changing in time. And that changing in time piece is really important because that should give us a clue that if we have magnetic fields and currents and loops, and something is changing in time, then we are most certainly going to have something to do with Faraday's law and Lenz's law. And once we get to the physics step, we'll see which equation those are and how to apply them. Alright, next step is our draw step. And give me a second to pull that up. Alright, so here's a drawing of what we have here. Now, here on the left side, this is a side view. We have the magnetic field in the direction from right to left, and the plane of our loop is in the plane of the screen. So right now you're looking directly through that loop, and it's rotating in time. So if we look at a top view, still we have the magnetic field going from right to left. But as we look at our normal vector from a top-down perspective, we can see that the vector is pointing in the down direction, whereas in our side view it's pointing out of the screen. So you get two different perspectives on the same problem, and on the top view the loop is going to be rotating counterclockwise. So the left side of the loop is going down and to the right, and our right side is moving up and to the left. Alright, so that's what's going on. Let's take a look at our given values. Alright, so we're giving the area of our loop, we're given the strength of the magnetic field, or the magnitude of the magnetic field, we're given the angle with respect to the magnetic field vector, and we're given the angular velocity of our loop, or how quickly it's rotating. Notice that we're given the angle in radians, and we're given the angular velocity in radians per second. So when we get to the actual calculation piece, make sure that your calculator is in radian mode. Alright, moving forward. Assumptions. We've already been told that we have a uniform magnetic field, and it doesn't say that the area is changing, so we don't necessarily need to assume that it's remaining constant. We could say that we're assuming that there's only one loop in the wire, but it mentions that it's a rectangular loop. It doesn't mention how many turns, so we're going to go ahead and assume that n is equal to 1. And we'll put that back down here in our givens. N is equal to 1. Any uppercase n is, in this course, generally going to refer to a number. If you look back to block 1 in our nuclear physics block, where uppercase N represented the number of nuclei that have not yet decayed, but still a number. Here in this block, in block 6, it represents the number of loops, whether we're talking about solenoids, whether we're talking about toroids, or we're talking about loops of wire with respect to Faraday's and Lenz's law. Alright, moving on. Next up, we have our tasks. And we need to calculate the induced EMF. Again, that's another indicator that we're going to be dealing with Lenz's law. And if we're working with Lenz's law, which looks at the time-changing magnetic flux, then we need to look at Faraday's law, which gives us our magnetic flux. Okay, let's keep moving. It's physics step time. I want you all to pause the video, and I want you to write down the equations you think you will need to solve this problem. Alright, see you in a minute. Alright, welcome back. So, because I've underlined and highlighted Faraday's and Lenz's law a few times now, that should have been an indicator that, hey, I'm going to need those equations. And so those are the first two equations I have. First one there is the magnetic flux. And the second one is the induced EMF, which is the electromotive force, the thing that's actually pushing the electrons in our conducting wire. And that's equal to the negative times the number of loops in our coil times the first time derivative of our magnetic flux. Alright, in this third one, because I mentioned that we have an angle changing in time, that means that our angle theta of our normal vector with respect to our magnetic field, because that's changing in time, we need to have an angle theta that is time dependent. Well, if we go to our PRC and look under the rotational kinematics portion, top portion, left-hand side, we will see this equation where our angle is a function of time as well as our angular velocity, in this case speed, and our angular acceleration. Alright, so we're going to keep that in the back of our mind until we get to the portion of Lenz's law where we actually will look at the derivative of our time-dependent angle equation. Alright, we need some space. Let's move on to the next page. Alright, first up is Faraday's law. We are looking at the amount of magnetic field going through a hypothetical surface. In this case, it's the amount of magnetic field going through our loop. That loop is bounded by our wire, and it's the amount of electric field going through the center of that loop. Okay. Now, how can we simplify this? Because that's what we want to do. We want to make this integral easy to manage. So the first thing we're going to do is take care of this dot product. So we can put our dot product in magnitude and angle form. And now we need to actually look at our integral. So the question we have to ask is, does our magnetic field depend on where in the loop we are looking? Because this differential area piece is just lots of little chunks of area inside our loop. And so as we add all those up, we should get the total area of the loop. But we have to be careful. Is the magnetic field uniform through that area? Well, it says so in the problem statement. So if it's uniform, then that means that it's the same everywhere. Now what about this cosine of theta term? Well, we know that theta is a function of time from our physics step and also from the problem statement. But the angle of our loop is not dependent on anything to do with the area. So we can take both our magnetic field and we can take our cosine of theta term out of the integral and put it out in front. And all we're left with is the sum of all of our little differential area chunks inside our loop. Now we just have the integral of our differential area. We're just adding up all these chunks. And so we're left with just the area times the magnetic field times the cosine of the angle between our area vector. Remember that we have our magnetic field traveling in that direction, and we have our normal unit vector pointing out of the screen or out of the page. So those are 90 degrees apart initially. Now we don't want to put in the angle between our vectors just yet. Okay, we want to leave it as it is. But before we do that, anytime we have a Faraday and Lenz's law problem or any type of induced EMF, you know, it's this phrase right here that gives it all away. Anytime we do, we need to identify what is changing in time. So let's take a minute and look at what could possibly change in time. Well, we could have a changing magnetic field. So our loop itself isn't moving at all, and it's the magnetic field that is changing in time. We could change the size of our loop in time, whether it's getting bigger or smaller. Or we could change the angle in time. And really, I said or, but really we could change all of those at the same time. But we're not quite that masochistic, well, sadistic. We enjoy the pain, but we don't necessarily enjoy watching you suffer. So we will only really change one of those variables at a time. So 3 possible changes, and it's that variable that changes in time that you need to identify early on. And it's going to make this process a lot easier. Okay, so now that we have laid out which variables could change in time, we see that our angle is going to change in time from our read step. And so now we're going to apply Faraday's law to Lenz's law. And that is, wrong color. That is the induced EMF, or the electromotive force, is equal to the negative number of turns in our coil times the first time derivative of our electric flux. Now we said that we assumed there was only one loop in our coil, so now we're just left with negative, and I'm going to make this substitution. The magnitude of the magnetic field times the area of our loop times cosine of our angle, and that's still all equal to the induced EMF. Alright, so how many variables do we have inside of our derivative? We have 3 variables, so we could potentially have 3 different terms when we do our chain rule. So I want you to pause the video, and I want you to do a full product rule or chain rule, whichever one you call it, on this term, or all these terms. So you should end up with 3, and we'll take a look at what you got. Alright, see you in a minute. Alright, so this should be what you got. My first term, I am taking the derivative of the magnetic field with respect to time, leaving the remaining variables constant. In my next term, my magnetic field is now constant, and I'm taking the derivative of my area with respect to time. And my angle of the normal vector of my loop, between that and my magnetic field vector. In the last term, my magnetic field is constant, the area of my loop is constant, but the thing that is changing is the angle with respect to the normal vector and my magnetic field vector. Now, sine of theta isn't a variable. Theta is the variable. So when I take the derivative of that cosine theta term, first I have to take the derivative of cosine theta, and that happens to be negative sine, which is why I have a plus here. And I have to multiply that times the derivative of the inside of our function, which is d theta dt. Alright, so of these three terms, which one sticks around? Drum roll, please. Well, let's look at the first term. The first term says that the magnetic field is uniform. Well, uniform only tells us that our magnetic field is the same everywhere. It's talking about the spatial dependency of the magnetic field. It doesn't say anything about the time dependency. It's not until we look at what the magnetic field is. It just says 0.2 Tesla, and that's it. No mention of anything changing. So we also know that it is the same in time. Regardless of what time we're looking at it, the magnetic field is constant. Well, if that's the case, then this term is out, because our derivative of the magnetic field is equal to 0. Let's look at our next term. Is the area changing with time? Again, it makes no mention of a time-dependent area. It just gives us a constant in the problem statement. Alright, well that tells us that that time derivative is also equal to 0. Now, what about our time-changing angle? Well, this tells us right away in the problem statement that we have a loop that is 90 degrees between the normal vector and the magnetic field, and it's increasing at a rate of 0.6 radians per second. The angle is changing with time. This is a non-zero derivative. So this one actually lives through our little analysis here. And this goes to show that, yes, we can in fact make all three things change with time. If the area was changing, if the magnetic field was changing, then all three of these terms would survive, and we'd have a much more complex problem. Thankfully we don't. So our induced EMF is equal to the magnitude of the magnetic field times the area of our loop times the sine of our angle times the first time derivative of our angle with respect to time. Okay, so let's go to another page, and I'll keep this equation here and bring it over to the next page. Alright, so here's where we're at. Again, our induced EMF is equal to the magnitude of the magnetic field times the area of our loop times the sine of the angle between our magnetic field and our area vector, and multiplied times the first time derivative of our angle function. Well, let's take a look back at our angle function. We said that from our rotational kinematics that theta minus theta naught is equal to omega naught times time plus 1/2 angular acceleration times time squared. Well, we have a constant angular velocity. If we have a constant angular velocity, then our acceleration term is out. We can also assume that our initial angle is also 0. So we're left with our time-dependent angle is equal to our angular speed times our time. Now, I want you all to pause the video, perform this derivative, and let's take a look at what you get. See you in a few seconds. Well, hopefully that didn't take you too long. Alright, so the first time derivative of our angle function is just our angular speed. So let's put that back into our beginning equation. So now we have the induced EMF is equal to our angular speed of our loop times the strength of the magnetic field flowing through our loop times the area of our loop times the sine of the angle between our magnetic field vector and the unit vector normal to the surface that is circumscribed by our loop. And for the time being, we'll just leave that as theta. This is our algebraic solution. From this point, we can just put in our given values. So the induced EMF is equal to 0.018 volts. Alright, we only have two sig figs here, the 1 and the 8, because we only have two sig figs throughout the problem statement. And our units are in volts, because our electromotive force is measured in volts. It's no different than a potential difference. Alright, that covers this problem for this lesson. I hope you take the time to go through all of these suggested problems for this lesson, because you get a chance to go back and take a look at all of the variables that could potentially change in Faraday's law. This one we were looking at the changing angle, but the other suggested problems look at a changing area, and another one looks at the changing magnetic field. So please, please, please go through those, not just for my sake, but for your sake. We do have the term end exam coming up, and you all haven't really been tested on a major graded event on this material. You can bet that some of this new stuff is going to be on the tee, so we can get our check on learning in. Alright, that aside, good luck on the homework. I will see you in class, and be Navy! Can't forget the cuteness tax. Here's our youngest supporting her army spirit, although she kind of looks like an alien. That's alright. I love her anyway. See you all in class.